So, hi everyone, welcome to this live session. So, we'll just wait for a couple of minutes. I think then we'll be starting at around 3 or 5 p.m. So, you must be aware this is the last live session of this course, but you may receive a mail in coming days. There will be one extra session scheduled, which is not confirmed yet, but it will be scheduled. I think around. Uh, I have given my consent to that, so I think it will be scheduled on 22nd. I'm not sure. We haven't received any confirmation yet, but there are plans. We'll have an extra session. So in that session, what I'm planning to do is take some problems that I've already discussed with you guys in the previous live sessions that I feel like needs to be discussed again from examination point of view. They might be important and all, and also there are those which will know lots of concepts and all which are quite tricky questions. I will discuss them again. And also, what I'll be doing is I'll make a list of some questions from this year's assignments that you got, and I'll pick them, just few of them, and I'll show their solutions. Maybe that will help you. And other than that, in that live session, we will discuss any other doubts pertaining to these problems, the pertaining to the problems in the course. We'll be discussing them also. So I think most probably it will be scheduled on next Sunday. But if not, anyways, this will be the last live session. But I feel like it will be scheduled on next Sunday. And in terms of course, if we talk about the course, this is the last live session. So I think it's already 3:05. I think we should start. So let me just share my screen first and then we can start. So, hi everyone. My name is Musayab Rafiq. I'm your course TA for the course Digital Circuits. I'm a PhD student in the Department of Electrical Engineering at IIT Kanpur. And this course, Digital Circuits, taught by Professor Shantanu Chattopadhyay from IIT Kharagpur. So this is the last live session, and I has already pre-advertised there might be an extra session, but in terms of the number of sessions that were scheduled for this course, this is the last. So as already announced in the last session that in week 12 also we have questions and problems related to the microprocessor 8085. So in today's live session we are going to discuss problems related to microprocessor 8085, and other than that there's nothing else to share. So I think I should start. So before I proceed to the main session or main problem section of this today's live session, I thought let me just give a quick overview of the pin diagram of 8085 microprocessor. So in the last lecture, if you remember, we discussed the brief overview of the architecture of 8085, and this time I thought let me just give a quick overview of this pin diagram of 8085 microprocessor. I won't go into details. In details, you can refer to your lecture notes and the books that I've already mentioned. I thought I'll just give the overview of the this Venn diagram. So if you talk about this microprocessor 8085, it has got 40 pins, right? You can see from the figure. So 20 from this side and 20 from this side. In total, we have got 40 pins. And if we talk about the classification, these 40 pins can be classified broadly into 7 categories. So number one is the data bus. So these are basically these A15 to A8. So total 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sorry, 1, 2, 3, 4, 5, 6, 7, 8. These 8 data buses that are from A8 to A15. Basically, they contain the most significant 8 bits of memory or input output address. So they contain the most significant bits of the 8 bits of memory and input output address. So this was first, that was the address bus. Then we have the data bus from AD0 to AD7. These are also 8 bits. It carries the least significant 8-bit address and data bus. So AD0 to AD7. Then the third one is the control and status signals. So they are used to identify the nature of operation. So what I told you, there are other set, that is the third set is control and status signals that are used to identify nature of operation. There are 3 control signals and 3 status signals. Number one, we have this RD signal. Basically, it is a signal that indicates the selected input output or memory device is to be read and is ready for accepting data available on the data bus. So what it does is it indicates the selected input output or the memory device is ready to be read and accepting data available on the data bus. Then we have this write WR. This indicates that the data on the data bus is ready to be written into a selected memory or input output location, right? And then we have ALE, address latch enable. It is a signal, basically. It is a positive going pulse generated when a new operation is started by the microprocessor. When the pulse goes high, it indicates address. When the pulse goes down, it indicates data. So in terms of what should I say, uh, control signals, there are three: read, write, and address latch enable, right? And in terms of then we have 3 status signals. These are input output IO or slash memory. This signal is used to differentiate between input output and memory operation. That is, when it is high, it indicates input output operation, and when it is low, it indicates memory operation here. And then we have S1 and S0 status signals. These signals are used to identify type of current operation here and here. This is S1 and S0 will also be here. S0 is here, right? Now after that, we have the power supply. There are two power supply signals, VCC and VSS. VCC indicates a plus 5 volt power supply and VSS indicates a ground signal. So the third group was this control and shader signals. We had three control signals and we had three shader signals. That was input output memory S1 and S0. Then we have the clock. There are three clock signals X1, X2 and clock out. X1, X2 and clock out. X1, X2 are used to set frequency of the internal clock register, while clock out here are used as system clock for devices connected with the microprocessor. Then we have the sixth group, that is the interrupts and externally initiated signals. So last time we also discussed briefly about these interrupts, their priority orders and all. So basically interrupts are the signals generated by the external devices to request the microprocessor to perform a task. There are five interrupt signals. These are trap, reset 7.5, reset 6.5, reset 5.5 and INTR. And then we have INTA. It is an interrupt acknowledgement signal. Then we have reset in. This signal is used to reset the microprocessor by resetting the program counter to 0. Then we have reset out. This signal is used to reset all connected devices and the microprocessor is reset. We have ready here. This signal indicates that the device is ready to send or receive data. If the ready is low, then the CPU has to wait for ready to go high. We have hold right here. The signal indicates that another master is requesting the use of address and data buses. Then we have hold acknowledgement HLDA. It indicates that the CPU has received the hold request and it will relinquish the bus in the next clock cycle. HLDA is set low after hold signal is removed. And also we have two serial signals, SOD, serial output data line here, and serial input data line. Serial output data line is set reset as specified by the SIM instruction, and serial input data line is basically data on this line is loaded into accumulator whenever SIM instruction is executed. So this was just a brief overview of this pin diagram of VT85. I just gave a brief overview what each of the pin does. So for details you can refer to your textbooks. So this architecture and pin diagram you should have at least an idea about these things. So let me just write down some important points that I already discussed. So there are 40 pins of 8085 microprocessor. Rather, I should write in there are 40 pins in 8085 microprocessor. Then these pins are broadly classified into 7 categories. Number one, address bus. These are right here. Number two, data bus. Right here. Number three is the controlling status signals. Control and status signals. So these are right here. Three, three. There should be one more. Yeah, this. So I think this VPP is your address slash enable. Let me just reconfirm. Just cross check with the figure that I have here. Yeah, pin number 30. So basically address slash enable. Yeah, this should be address slash enable. Let me just check. Yeah, this should be. I think this should be your address slash enable. You guys can confirm this should be your address slash enable. I think. And after that we have power supply. This is here and this is here. Then we have clock signals. So these are your X1, X2 and clock out. Then you have interrupt and externally initiated signals. Interrupt and externally initiated. These are your interrupts. So trap and so on, RO6. And then you have hold acknowledgement, reset and reset out ready. And then your last one are two serial signals. These are your two serial signals. I think all of them got covered. Yeah, I think VPP is your address latch enable. So this was about. So this was about the pin diagram of 8085 microprocessor. To the students that joined late, I will discuss this thing at the end again. So this is the brief overview that I gave of this pin diagram of microprocessor 8085. Just the how many pins are there, or in which categories we divide them. If time permits, I will discuss this thing again at the end. Just a brief overview. I didn't go into details. I just gave the overview of the pins and all, and which signal does what. So you all can have a look at this at the end. We can have a look at this and again. So now I think we are ready to go to our main topic of today's session. That is basically the problem solving that we usually do. So we start with the question number first. So what we have here is it says that accumulator has data ffx hex, basically ffx. So now the question asks us to determine the state of carry flag, the zero flag, and the sign flag when two operations are executed. So number one operation is when zero hex, zero one hex is added, and number two the content of the accumulator is incremented. So how will you do it? So what we have here is we have contents of the accumulator as ffx, right? And we need to figure out the status of these three flags: carry, zero, and this. Let's just discuss operation first, that is adding one to accumulator. So a, which is your ff, can be written like 1 1 1, 1, 1, 1, 1, 1. Now the operation that is being executed is addition. So we'll add 1. So 1 plus 1 is 2, that is 0. Again, carry will be here. 1 plus 1 is 2, 1, 0. Carry will be here. 1 plus 1 is 2. So what will happen is it will propagate, carry will propagate up to here. And then again 1 plus 1 is 2. So it will be like this. And we have a carry here. So my carry will be 1. My 0 flag will be 1 because the contents of accumulator are 0. And one more thing, since it is no negative, we didn't get any negative number from the operation. So what we'll have is my sign flag will be 0. So in operation 1, we have, so actually there was some problem with the recording. I think question number 1 last part was not recorded, so I'll just re-record it again, the last part only, and then I'll show the question number 2 also. So I guess some of you have written the answer. So let me just show the question number 1 and 1 again. So in the end, maybe I'll just have question number 1 in the end again, when I'll just recap the pin diagram thing. So till then, you guys can do this. Let me just share. You guys can do this thing. Have you guys solved this question number 2? Anyone? Anyone else? So let me just show you the solution to the question number 2. So question number 2 asks us an 8085 microprocessor accesses two memory locations 2001 hex and 2002 hex that contain 8-bit numbers 98 hex and B1 hex, and then the following program is executed. So what we have here is, we have the first instructions LXI X, LXI H 2001 hex. So basically HL goes to 0, L goes 01 hex, right? Because of this instruction LXI. Then we have MVI-A, that is move immediate A 21 hex. So accumulator A gets loaded with 2 hex, 21 hex. That is 0 0 1 0 0 0 0 1, right? Then what we have here is INXH, that is the increment operation on H, HL pair. So that is HL plus 1. That thing is H goes to 20 hex and L goes to 02 hex, right? And then your HL has the memory location that is 2002 hex. Then you have add M. This here is basically what this operation says is add to the contents of accumulator the reference date of HL pair. So what is the reference date of HL pair? So right now HL is storing the memory location 2002. And what is the data stored at 2002? It's B1 hex. So B1 hex. So I have to do A, that is A is having 21, so 0 0 1 0 0 0 0 1, and my memory location is having the data B1. So 1 is 0 0 0 1, B is your 11. So 8 plus 2 plus 1, so it's 1 0 1 1. Another addition will happen, so it's 1 plus 1 is 0, 1 carry will come here, so 0 0, then it's 1, 1 plus 1 is 0 1, then 1 0. So it's sorry, it's 1 1 0 1 0 0 1 0. So this is 8 plus 2 is 10, 10 plus 8 plus 4 is 12, 12 plus 1 is 13. So 13 is D, and this thing is 2. So D2 hex is the result of your operation, and this will be in your accumulator, right? Now after that, what we have here is we have the increment operation again on INXH on H. So HL will become 2003, because initially it was 2002. Now it will be 2003. Now what I am doing after that, I'm moving the contents of accumulator to the memory referenced. So the memory is 2003. So in 2003, my D2 will be there, this thing. So D2 will go to 2003. So now I just simply need to write the D2 hex in binary, sorry, in decimal. So it is 16 raised power 0 multiplied by 2 plus 16 raised power 1 multiplied by D is your 13. D is your 13 or 14? 10, 11, 12, 13, 14, 15. D is your 13, I think. Yeah, uh, D is your 13, yes. So 16 into 3, 13 is basically 160 plus 160 plus 48 is 208. 208 plus 208 plus 2 is 210. So the at the end of the program, the memory location 20 contains a number in decimal, that is 210. Any doubts in here? Any doubts in here? Were you able to do it initially? So I think we can progress. Are there any doubts I'm missing again? Anyways, we can just refer to these type of questions at the end again. So let me just go to question number 3. So this is an interesting question. I would like you guys to take a look at this first, and then I'll show the solution. So it states that which of the following 8085 microprocessor programs correctly calculates the product of two 8-bit numbers stored in register B and C. So among the following four operations, you need to figure out which of them does the correct multiplication operation. So I'll just give you a couple of minutes. You guys can take a look and write down your answers. Anyone else? So I forgot. Someone had written an answer 2023 to previous question. I hope you got the explanation how we approach the problem. I hope you got it. And anyone tell me, okay, just a second. Anyone else has figured out which is the correct instruction or a program to do multiplication of two numbers stored at a memory locations in registers B and C? Anyone else? So one of the participant has given the correct answer. So basically in microprocessor 8085 we don't have a direct multiply instruction. So what we take help of is the addition condition, addition instruction or operation. So we basically utilize this addition operation and we take help of this addition operation to get to the desired multiplication. So if you want to, let's say, add two, multiply two numbers A and B without having direct multiple option, what we do, we add B to A, we add A cumulatively B number of times. So what I mean to say is, if we want to multiply 2 and 3, what we will do is we will add 2 to itself 3 number of times, or 3 to 3 to itself 2 number of times. So this will give 6. So what if I want to add A multiply B? So we have to add A, so on up to B number of times. So this is your required operation. So among the following instruction, which when does it? It's as rightly pointed out by someone. It's instruction 3. That is the program 3. So what it does is it basically resets the accumulator first to 00 hex. Then loop starts here. So it adds C. So C gets added to this. C gets added. That is addition of C with A. That is C in first iteration. It's C itself. Then the contents of then the register this we have a decrement operation and B gets decreased by 1. Then again C gets added and B gets decreased by 1. So on up to it when it becomes 0. So that means C plus C plus C will happen B number of times. So that is your required multiplication. Basically what it does, it adds C, then the contents of B get decremented, then it's again C, then again, so on up to when B becomes 0. So this C got added to itself B number of times. That is your multiplication operation. So this was about question number 3, where we discussed how we can take the help of an addition operation to do multiplication operation in 8085, because we don't have a direct multiplication operation in 8085. Any doubts in here? I hope it was clear. Now, what we have is that is question number 4 of today's live session. So, it asks us, a trap is a maskable highest priority software interrupt. Number 2, non-maskable highest priority hardware interrupt. Number 3, non-maskable highest priority software interrupt. Number 4, maskable lowest priority and hardware interrupt. Number 5, non-maskable lowest priority software interrupt. So before we proceed to the answers, I'll just write a few points. So we have basically these interrupts. As you also we have the interrupts. There are two types of interrupts. First is the hardware interrupt, and second is your software interrupt. In hardware, we have maskable, and in another, we have non-maskable. For more details on this maskable and unmaskable, you can refer to your lecture notes. If you don't find in them, you can refer to your textbooks. And software interrupt, there are no further types. So what this trap is basically, it is a non-maskable hardware interrupt which has got the highest priority, right? This thing regarding highest priority we discussed in last live session also. So what we have is trap is the highest priority non-maskable hardware interrupt. So option 2 is your correct answer. So when a microprocessor receives interrupt signal through pins, that is hardware, they are known as hardware interrupt, right? So order of priorities, trap is greater than reset 7.5 is greater than reset 6.5 is greater than reset 5.5 is greater than INTR signal. Now, this is another question, theoretical question. It states that an interrupt in which external device supplies its address as well as the interrupt request is called. So, external device supplies its address as well as the interrupt request is called, interrupt signal is called, is the vectored interrupt. So, basically, in vectored interrupt, in this type of interrupts, the intercepting device directs the processor for intercept service routine, and in maskable, an interrupt whose interrupt service can be stopped from being serviced temporarily is called maskable interrupt. And interrupt whose service cannot be delayed is called non-maskable. So I'll repeat again. Vectored, in this type of interrupts, the interrupting device directs the processor for interrupt service routine. Maskable, in this, an interrupt whose interrupt service can be stopped from being serviced temporarily. Non-maskable is an interrupt whose service cannot be delayed. Now we have the question 6 here. It states that choose an incorrect statement from the following regarding pin numbers of 8085. So for a reference, I have put this pin diagram of 8085 here. In exam, you don't have this liberty, but right now I'll just put here. So we need to choose the incorrect statement out of the following. So number one is basically serial input output ports are 5 and 4, reset out and clock out are 3 and 37. So basically these are the pin numbers. Ground and VCC are 20 and 40 respectively. Interrupt and trap are 10 and 6 respectively. Reset 6.5 and reset 7.5 are 7 and 8. So if you let's take a help of this pin diagram. So serial ports are 5 and 4. So serial ports are 5 and 4, correct? So this is correct. Reset out and clock out are 3 and 37. Reset out and clock out are 3 and 37, correct? Ground and VCC are 20 and 40 respectively. 20 is ground, VCC is right here, 40. Interrupt and trap are 10 and 6. Interrupt and trap are 10 and 6, correct? And finally, reset 7.5 and reset 7.5 are 7 and 8. Reset 7.5 is 7 and reset 6.5 is 8. So this is wrong. It should be reverse, like this. So option 5 is your correct option. So any doubts in here? So this was 2. So you guys have written 2. I think it was for question 5, right? I hope that was clear, right? So now let's discuss the next question of today's live session. So the next question of today's live session is, what is the length of stack pointer? Anyone? One of the student has correctly pointed out. So the length of stack pointer is 16 bits. That is option 4. So basically what this stack pointer is, it is a 16-bit register that stores the address of the top of memory stack. So value of stack pointer is decremented by 2 in push and incremented by 2 in pop. Few participants want to join. Let me just admit them. So as rightly pointed out by one of the participants, so option 4 was the correct answer. Now what we have is question number 8. So can anyone tell me what will be the correct answer to this question, which says that in 8085 microprocessor, which signal is used to insert weight? Can anyone tell me which signal is used to insert weight? Sometimes your answers are not that obvious. So you guys thought hold is means wait. So sometimes they are not quite obvious. One of the participant has written the answer. So hold, it's not a direct English synonym you are using here. So the correct answer is ready. The ready signal introduces a delay. So let me just mark this. So the ready signal, that is option 1, is used to insert wait. So basically what this ready signal is, it is used to delay the microprocessor read or write cycles until a slow responding peripheral is ready to send or accept data. So when this signal goes low, the microprocessor waits for integral number of clock cycle until it goes high. And for a hold signal, so we are two in hold signal, that is hold and hold acknowledgement. They are used in the DMA operation, and when the hold signal goes high, it indicates that the processor that another master is requesting the bus access. The process after receiving the hold request issues the acknowledge signal on the HLDA pin. So it's basically the ready signal that is used to introduce the delay, that is used to insert the delay time. Now we have this question here, question number 9. The program status word register pair is made up of. Question number 9. Program is made up of. Anyone else? Yeah, option D is correct. So the program register word status word register pair is made up of accumulator and the flag registers. Then this thing 8086 is a dash bit processor. How many bit processor is 8086? So a couple of students have already given the answer. So it is a 16-bit processor. So then we have question number 11. It states that the trap interrupt transfers the control to location. So it transfers the control to which of the locations? So the trap interrupt transfers request to which of the location? Control to which of the location? Option A 24 hex, option B 2C hex, option C 34 hex, option D 3C hex. So basically it transfers the control to the location 24 hex. So the ISR interrupt service routine request address for trap is 0024 hex. Then this is a question I would like you guys to do first, then I'll show the solution. And these are the questions we did extensively in the last live session also. So this states that an 8085 assembly language program is given below. Assume that carry flag is initially unset. The content of the accumulator after the execution of the program is. So I'll just give you 5-6 minutes to do this question, and then I'll show the solution. Are you guys doing it, or has anyone done it? They can write the answers in the chat box if they have done it. I don't think it's that difficult. It's a pretty simple question. I was expecting at least a couple of participants would have given answers by now. But I guess no one wants to pick up a pen and a paper and do this question. Anyways, so an 8085 assembly language program is given below. Assume that carry flag is initially that the content of the accumulator after the execution of the program is. So move immediate A. So A gets, that is accumulator gets loaded with 7. That is 0 0 0 0 0 1 1 1. Then that we have rotate left. So we have rotated left. So it will shift by one position. So it's 0 0 0 0 1 1 1 0. That is 8 plus 4 is 12. 12 plus 2 is 14. So that is E0 E hex. Then we have moved B to A. So B gets this thing 0E. Then we have again RLC. So we have 0 0 0 1 1 1 0 0. Then again RLC. So it's 0 0 1 1 1 0 0 0. So this is your content of accumulator 0 0 1 1 1 0 0 0. Then you are adding B to it. So B has 0E. So basically add operation will do 0 0 0 0 1 1 1 0, and you have to add 0 0 1 1 1 0 0 0. So this is 0 1 1 0 0 0 1 0 0 1 1 0 0 1 1 0. Now these are the contents of accumulator. Now we have the last instruction, that is RRC. So RRC, so it will go like this: 0 0 0 basically 1 0 6. So it will be 0 0 1 1 0 0 1 0 0 0 1 0 0 0 1 1. So this is 2, this is 3. So 2 3 hex will be my content of the accumulator, contents of the accumulator after the execution. So option 3 is the right answer. Only one of the participant is taking active has any inactive participation. All others are just anyways. It's your choice. I can't force anyone. So now question number 13 needs to be discussed. So again, I would like you guys to do this first. It's a matter of only a couple of minutes. I hope you do this time. So the contents of the accumulator after the execution of the following instructions will be. So first we have move immediate A B7 hex, then we have OR operation, then we have rotate accumulator through left. Rotate contents of accumulator left through carry. So that is RAL. So what will be the contents of the accumulator after the following set of instructions are executed? Suresh and Venkata, your first digit is correct, but your last digit is basically the second part is wrong. I guess it's because of RAL. You did what you did is RLC. Yeah, 6C is correct. Let me just show you. So what we have is first A gets loaded with this B7X. So that is B is your level 1 0 1 1 1 0 1 1 and 7 is your 0 1 1 1. Then OR of A. So basically OR operation of A with itself. So it's 1 0 1 1 0 1 1 1 1 0 1 1 0 1 1 1. So that is 1 1 1 0 1 1. So that is 1 0 1 1 0 1 1. Basically, you can take the direct help of this property A or with A is simply A. Now what we have here is rotate accumulator left through carry. So one thing, whenever we have OR operation, carry flag is 0. So we have to shift this thing with left. So this will go 0 1 1 0 1 1 1. So this thing, now this bit is 0. Basically RAL is like this: D7 D6 D5 D4 so on up to DU0. This is your carry. In RAL everything will go shift by one position towards left. D7 will go to carry and carry will go to D0. So this is your 6 and this is your 8 plus 4 is 12, 12 plus 2 is 14. So this is E. So this thing is 6E. I hope you found your mistakes, right? Now we will discuss question number 14. So you guys do it first. So the question is find the content of accumulator after the execution of following program. So you need to find out the contents of accumulator after the following set of instructions are executed. That is option. Okay. So let me just show the solution. So first instruction is MVIA F0. So that is A gets loaded with this F0. That is 1 1 1 1 0 0 0 0. Then we have OR immediate ORI FF with X. So this thing is, that is OR of, OR of contents of accumulator with FF. So it is 1 1 1 1 1 1 1. Now we have XRI F0, that is XOR of this thing with this, basically 1 1 1 1 1 1 1 needs to be XORed with this. So in XOR operation, when two bits are equal, it's 0. When two bits are different, it's 1. So the result will be like this: 0 0 0 0 1 1 1 1. That is 0 F X. That is option 3 is the correct answer. Where? Yeah. So basically, I have to do XOR of FF with 0. FF with, basically, I have to do XOR of FF with what thing? F0, right? So after, basically, let's go step by step. So in step 1, that is MVIA F0X, right? So the contents of accumulator are loaded with F0. Am I audible to you? Can you confirm? Yeah, I think there is some connectivity issues. Am I audible? Am I audible to you in particular? Yeah, you got the solution. Okay, that's right. So now let's go to question number 15. The stack pointer always points to anyone. Okay, the stack pointer always points to top of the stack. Now, next question. What happens when the below instruction is encountered by the 8085 microprocessor CNC 4001 hex? Anyone? Yeah, that's right. It is option B. Call the subroutine located at 4001 hex if carry flag is not set. Then I have this question. Which of the following instructions controls the interrupt enable flip flop? There are basically two signals that control. One is EI, another one. Can anyone tell me which is the other one? EI and option B is correct. That's right. There are two signals, two instructions. EI, EI and DI. Other is DI. DI, DI. Okay. EI and DI. Then the next question. Which of the following instructions is equivalent to call 0028 hex? Anyone? Which of the following instructions is equivalent to call 0028 hex? Yeah, option B. I saw some. Yeah, option B is the correct answer. So basically, when a reset 5 instruction is executed, it transfers the program execution to the appropriate entry in input vector table. The vector address is 5 into 8, that is 40, which is 28 hex. So this is instruction. So this is similar to the instruction call 0028x. So again, I'll repeat: when a reset 5 instruction is executed, it transfers the program execution to the appropriate entry in input vector table. The vector address is 5 into 8, that is 40, that is 0028x. So this thing is equivalent to this. Then question number 19. How many T states are required by ATT microprocessor to execute CNC instruction? Yeah, correct. Option 18 is right. Then I have how long must interrupt remain high to be sensed by ATT5 processor? Yeah, correct. I know other TAs discuss these problems. That's why you guys are very well versed with these problems. The rest of the problems, we don't have that material. So basically, I was a course TA for last sem also. So I have that problem set. That's why I bit. Yeah, yeah. What's the answer? So the following is not a yes. And which group of instructions do not affect the flags? Yeah, that's quite obvious because arithmetic and logic operations affect the flags. We have seen in multiple examples that we did. What is the size of Q present in 8086 microprocessor? Yeah, basically a group of first in first out in which up to 6 byte instructions code are refreshed from the memory ahead of time. Then this, yeah, yeah. In 8086 microprocessor, which of the following registers can be combined together to use an AL and AH? Okay, now this thing in which of the following is performed by execution unit in 8086? So AU executes the instruction already fetched by the bus interface unit. So this was all for today's live session. But what I will do here is because at the start of the live session, my recording system went into some trouble. So I guess the pin diagram part I had to repeat anyways. So the pin diagram part, that is a brief overview of the pin diagram that I gave. That is just spelling out the numbers and the, how many classifications are there. And question 1, 2, I'll just repeat here. And other than that, let me just repeat those things and then we can have some brief discussion. So I'll repeat the pin diagram part. Some of you were not present that time, so this is kind of a blessing in disguise. So I'll repeat the pin diagram part and also the question 1 and 2 because I assume they are not recorded because my recording system went into some trouble. So I'll repeat those two parts and then we can have some discussion, brief discussion. So basically, what I discussed in this pin diagram part. So last time we discussed the brief overview of architecture, and this time I'm discussing the pin diagram. So from a theoretical point of view and the conceptual point of view, these things are quite important, these architecture and the pin diagrams. So I'll just give a brief overview here. So this microprocessor 8085 has in total 40 pins, right? And they are broadly classified into 7 categories. Number one is the address bus. So these are from A15 to A8. It contains the most significant 8 bits of memory input output address. Just a second, someone wants to join now. And so they contain the most significant 8 bits of the input output address. So these address bits. And then we have the data bits. So it contains the least 8 significant bits. So AD0 to AD7. Then we have the control and status signals. There are in total, they are divided basically, we have control and status signals. They are used to identify the nature of operations. There are three control signals and three status signals. The control signals are read, write, and ALE. So the read signal indicates the selected input output or memory devices to be read and ready for accepting data available on the data bus. Write is the signal indicates that the data on the data bus is to be written into a selected memory or input output location. Then we have address latch enable. It is a positive going pulse generated by a new operation started by the microprocessor. It goes high and indicates address. When the pulse goes down, it indicates data. And then we have also the three status signals. These are input output memory, S1 and S0. Where are S1 and S0? The input output memory signal is used to differentiate between the input output and memory operations. That is, when it is high, it indicates the input output operation, and when it is low, it indicates the memory operation. Then we have S1 and S0. These are the signals used to identify type of current operation. Then we have a fourth set, that is a power supply. There are two power supply signals, that is the ground and the VCC. VCC is the plus 5 volt and VSS is your ground. Then we have five the clock signals. These are X1, X2 and clock out. X1, X2 is used to set frequency of the internal clock register, while the clock out is used as system clock for devices connected to the microprocessor. Then we have interrupts and externally initiated signals. So these are your interrupts, are signals generated by the external devices to request microprocessor to perform a task. There are five interrupt signals: trap, RST 5.5, 6.5, 5.5, and interrupt. And we have also these INTA, that is interrupt acknowledgement. Reset in is used to reset the microprocessor by setting the program counter to 0. Then we have reset out. This signal is used to reset all connected devices when the microprocessor is reset. We have the ready signal. It is a signal that indicates the device is ready to send or receive data. If ready is low, then the CPU has to wait for ready to go high. Then we have the hold signal right here. There is the hold right here. It is a signal that indicates another master is requesting the use of address in data buses. Then we have HLDA, that is a hold acknowledged. It indicates the CPU has received hold request and it will relinquish the bus in the next clock cycle. HLDA is set to low after hold signal is removed. Then we have two serial signals, that is SOD and SID. So this was just a brief overview of the pin diagram of the microprocessor 8085. Now I will repeat this question one here. Let me just use some. Okay, basically to decouple your read or write path. So multiplexing will require another circuitry, right? So what's the fun? Hmm. So which one more pin? So basically I am saying that a read its signal indicates that the selected input output or memory device should be read and ready for accepting data on the data bus. So yes, yes, but maybe you can have that, you can explore that thing, or maybe you can refer to your I'm not basically it's been a long time since I've gone through this 8085, but I think you need an extra circuitry then, I guess. So you are saying low will signify read and high will signify write, right? Maybe some other things are going in there. Your point is quite valid, but maybe some other things might be going there. Anyone else? It's a good question. Anyone else knows the answer to this? Let's have a discussion here, right? Maybe you can refer to some notes and maybe some books. See for the explanation. Right now, I don't have a correct explanation because I'm not. I have only gone through these lecture materials. From that, I don't have any explanation to your question, but it's a valid question. Let me just find out, because next week we are going, as I already said in the start of the lecture, we are going to have a what should I say, the extra live session. which is planned for the next Sunday. Maybe it's not confirmed right now, but most probably you will receive a notification about that. So let's discuss till then. If I find the correct explanation, we can discuss regarding this. Now we had this question number one. So this asked us. So where is it? It states that accumulator had data ffx, and we need to determine the state of carry flag, zero flag, and sign flag when two operations are performed. Number one was the one was added, 1x, and the content number two operation was the contents of the accumulator incremented. So adding of one to accumulator. So ff was the contents of accumulator, that is 1 1 1 1, and 1 was added to it. So when you add 1 to ff, so it became 0 0 0 0 0 with carry as 1. So carry was 1, your sign flag was 0 because it was not a negative number, and your 0 flag was set to 1 because the contents of the accumulator are 0. So after first operation, carry was 1, sign was 0, and z was 1. And next operation we had contents of accumulator are incremented. So when we have this increment operation, it does not have any effect on the carry flag. So the contents of accumulator from FFF are incremented, it will become 0000. So once they become 000, the zero flag is set to 1 and the sign flag is 0, and the carry flag is don't care, that is previous state is maintained. So option 2 is the correct answer to this question. And also I had this question, that is question number 2, which stated that an 8085 microprocessor accesses two memory location 2001 hex and 2002 that contain 8-bit numbers 98 hex and B1 hex. The following program is executed. So LXI hex to HL 2001, that means H is 20 and L is 01 hex. MVI A21 hex, so accumulator gets loaded with this 21, so that is 0010000001. Then is increment of hex, INX hex, so HL plus 1 operation that is basically happening. So H is 20, L will become 02, so HL is 2002 hex. Then add memory, so add M. So basically this means add to the contents of accumulator reference data of HL pair. So reference data of HL pair is the data that is stored at the memory location 2002. So at 2002, B1 is stored. So to the contents of accumulator, that is 21 00100001, B1 is added. So 1011 1011 0001. So after addition, this became D2 hex right here. So A gets D2 hex, and then the contents of A are moved to the memory location. First increment is done. So HL was 2002, it became 2003 here. Now contents of accumulator are moved to the memory M, so that is 2003 will have this D2, and D2 when converted to decimal became 2010. So the answer was 210 in decimal. Let me just take a look. Yeah, yeah. No, no. Basically, whatever there was in accumulator, right? So accumulator was loaded with FF, right? You have to look at the start. Accumulator was located at FF. Now you are incrementing it by 1. So what will FF become? No, 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 no. These are two separate operations. Oh, oh, yeah, 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 yeah. That's a valid confusion that you had. Yeah, that's true. These are two separate operations. Basically, FF gets added with 1, FF gets incremented. That's all. Yeah. Hmm. Hmm. So I think. Hmm. Yeah, yeah. Continue, please. Hmm. Okay. Thanks for clarifying. Thanks for clarifying. So can we just say we can have a same pin, but we will be giving this to avoid the confusion. We'll be giving this T-state penalty, increasing the time. Can we say it like that? O- Okay. Oh, mhm. So that's what I'm saying, that we had this time penalty and now our processing speed is quite high, so we are able to do it. Separate them. Yeah. 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 That's true. So that was all for today's live session. So what we'll do, we'll have an extra live session most probably on next Sunday. If not, then it's the last live session. I thank you guys for joining. This was my second time I was teaching this. In fact, solving these problems during the live session. And thank you all for your participation. I hope I did justice to this course. So I'll be again taking up the course next time. I don't know which course they will allocate me, if at all they are allocating to us again. So that was all. And one thing to the students, I know some of you are uh, teachers, professor, lecturers, and I'm not referring to them. I'm referring to the students. They are bachelor students and all. So what I saw, what I inferred from your these live sessions, and also to the people that are watching the video lectures. So the questions that are discussed earlier by some TAs, you guys were able to solve them. Basically, you had memorized those answers, or you have understood them. But once a question along those lines is given to you, most of them were not able to solve it. I think you need to focus on them. You need to focus on your understanding. So basically, all questions usually follow same pattern. If your concepts are clear, how we approach a particular problem and how we are approaching the problem again, you'll be able to solve them. So once we are solving these problems, see what we are doing. The next problem is not difficult. The unseen problem is not difficult. It's just another variation of that. So always take a clear look what we are doing. Just memorizing the steps, just following what your professor, your teacher, or your, let's say, IMT or TA does, will not help you. See why are we doing those things and what are the operations that we are doing is quite important, because next time whenever you face an unseen problem, you may not be able to do it if you have not done practice properly. So practice is quite important, and seeing what we are doing is also quite important. So, anyways, I'm quite happy with the response of this group this time. In fact, attendance was also quite appreciable, despite there being three TAs. So, thank you guys for joining. If you get time, do attend the extra live session next week. But it will be mostly discussing the previous problems only, and I hope I can pick some assignment problems also. Other than that, I think we are all done for today's live session and for the course also. Thank you guys for joining, and to those appearing in the exams, all the best for your exams. Thank you.